First thing we're going to do is I'm going to make a call for the 3 students that did not put their name on the, I think there's one more here. There's 2 students that did not put their name on. Can you turn it to the doc cam, please, Andrew? All right, so who belongs to this one here? First, is it? Okay, come on, put your name on it. Okay, good going. And Salim, does this look like yours? All right. Answers. All right, come on. Salim, come on up here, put your name on it. Come on. What am I supposed to use my laser eyeballs to engrave your name on it? Good. Yep, thank you. Now I could get these all graded up and stuff. All right, now we're cooking. Thanks. All right, can you put this in my knapsack? And switch over to laptop, please. Okay, students, what we're going to talk about today is chapter 23. And let's just switch over to the regular computer, please. Okay, so this is 23.1, induced EMF and magnetic flux. And you can see I've done a little bit of annotation in here. Here's my little comment about the Grand Coulee Dam. And then the next section is Faraday's law of induction and Lenz's law. And we're going to work on this. We're going to do a little calculation of this stuff in here today. And we're actually going to work with this diagram. So go ahead and switch back to the laptop, please. All right, so that's kind of what we're talking about today. And the guy that figured out most of this stuff and made the discovery was Michael Faraday. And Michael Faraday is an interesting guy. He is, so this is back in the early 1800s when he rose. And he was the son of a blacksmith. Now in England in those days, that was like being a peasant. And going to UCF or going to Oxford or Cambridge was like going to the moon. And in fact, he never did go to Oxford or Cambridge. He started out his working life as a young man, teenager, as an apprentice, the way many people did, to a bookbinder in London. But he had a great interest in education for all things. He tried to, like many people in those days that couldn't go to college, they educated themselves. And I know that's kind of a foreign concept to a lot of you guys. You feel like you're forced to go here to UCF by various individuals or whatever, but in actuality, this is a voluntary association here. You're here because it is your volition to be here and to educate yourself. Why I still have to nag you about homework and study, I do not know. But anyways, in these days, the common flow of people in London and other big cities, Paris, etc., they formed associations. Like the YMCA, Young Men's Christian Association, YWCA. All those associations. They formed associations to hear lectures by people to educate themselves, scientists, writers, mathematicians, all that kind of stuff. That's what so they formed their own like little study group, and some of them became big and famous. Faraday was a member of an association, and he attended. And one of the speakers was a famous chemist of the day, and he wrote he went to all that guy's lectures, and he took lecture notes. And then what he did was he spiffed up his lecture notes, and he made a hand-bound volume of them and gave it to the speaker after the speaker's series of talks was over. And he so impressed that chemist that he hired Michael Faraday as his personal assistant. You know, like his secretary, you know, doing this and doing that. And eventually, Michael Faraday began assisting him in the lab. And then after that, Michael Faraday broke away, and he found his way into the Royal Institution in London, and he became famous in chemistry and physics in his own right. He never learned calculus. Everybody in here that's had calculus class, and even if you haven't, even if you've just had trig class, you probably know more math than Michael Faraday did. And yet he was one of the smartest guys to ever walk the planet. And what he did was experimental measurements and discoveries, and he designed things. All of our generators and motors, electric motors and generators, are based on what he saw. He's the guy that nabbed it. And just think about all the electric motors that you use in your life. All the everybody in, you know, the lights are on here because somewhere a big generator is spinning, creating alternating current. You know, whether it's down at Port St. Lucie or somewhere else. You know, it's on the grid and stuff, but that's all from Michael Faraday. So let's take a look at the stuff that he saw. All right, here's his device that well, this is not his device. You can actually look at photos of his actual device. He had an iron ring, and this looks like an iron disc with a hole in it. And what he did was he put 2 independent coils on that ring, and one of them was hooked up to a current source, which you can see here represented as a battery. And that current source had a switch. You can see that at the very top. All right. And then the second loop of wire, the second coil, you can see that down here. Let me get my cursor over there. All right, that's down here. Now these 2 loops are independent of each other. You know, I shouldn't say they're independent of each other. As circuits, they're not connected. All right. But what does connect them is the magnetic field induced by the electromagnet in the upper loop. And because there's going to be field lines. And because it's in an iron ring, the field lines are going to tend to stay in the iron and form loops like what you see there. All right. Now the lower loop was hooked up to a meter. Now that device they show over there, a galvanometer is what it's called. That was Faraday's Fluke. All right, he used it for everything. All right, and basically what that was, it was another little electromagnet. I mean, everybody already figured out about electromagnetism. You put some current through a coil, you'll get a magnet. If you have another magnet nearby, it'll move. All right, and the galvanometer was designed to do that, pick up very small currents and move the needle. And so that's what so now here's the thing about it. Why should a magnetic field inside that lower loop, how's that lower loop ever going to get any current? It doesn't have a battery. It doesn't have jack. In those days, nobody knew about generators. They didn't know. But that's what Michael Faraday found. So he has this single piece of iron that basically forms the core of both coils. And you can look up a photograph of his exact device. They preserved it in a museum at the Royal Institution in London. and then you close the switch. And what happens is the second coil's meter jumps. And Michael Faraday figured out that previous to the switch being closed, there were no magnetic field lines anywhere. All right, it was an unmagnetized piece of iron. All right. You turn on the upper coil, you have field lines through it, of course. It's an electromagnet. But what nobody figured out until this experiment was that if you push new field lines through those secondary coils, bam, you get a current. And that's how we still do it. You know, this is we don't do it in this device. This is the discovery device, and now we have big, huge generators that, you know, you spin a magnet or a coil, and you know what you do to get it to spin. You know what you use? You use steam in a big nuclear or coal-fired or petroleum gas-fired power plant. Hydroelectric dam like Grand Coulee Dam use the falling delta P per second of falling water through the reservoir, through the top of the reservoir, and the generators are all down at the bottom of the below on the downhill side of the dam, the dry side of the dam, and as far down as you can get them. Okay, and you can see that in the picture of Grand Coulee Dam that I pasted into the textbook. All right, now here's his law. This is the law of induced EMF, electromotive force, and i.e. voltage. And we're going to do some calculations with this. And it's basically this: EMF is equal to minus N. N is the number of loops in your coil, times delta phi over delta T. And delta phi is defined as the flux. Okay, so here's, you know, we were jiving about flux earlier in the semester, and we were actually using flux concepts. Here it is. It's the amount of field lines poking through a little element of area for a given loop. So for instance, so in this, dA is a little teeny tiny pixel of area perpendicular to the magnetic field vector. All right. So, and this is how Michael Faraday thought of it. He was thinking of field lines as physical objects, not that you could see, but that you could detect with, for instance, a galvanometer. So he said, it looks like the more area I have, the more current I'll get. Okay. And the stronger my magnetic field is, the more current I'll get. And the shorter my delta T is, which for a switch is going to be pretty short, the bigger my current is going to, you know, the bigger my EMF is going to be. So he was thinking in terms of EMF, in terms of voltage. Now you can relate this to current as well. So flux defined as the sum of all the BDA for a given loop. So just pixelate your loop, and it can be a loop of any shape. And there's a ton of, you know, in that one sentence that I've got there, I've got a lot of words in there. And it's a shorthand for a ton of calculus, multidimensional calculus in 3 dimensions, and therefore a lot of trig. So Ashley, it's an act of kindness for me to not put the calculus for me in there. But there's a lot of calculus in there, and we can work out calculations from that, and we'll be doing that in just a minute. And as I mentioned, all of our modern day motors and generators are based on that. And even something that we have been talking about for decades now, the railgun, which is a device. Here's a picture of it. There's the railgun. That's a prototype out in Utah. And they're going to try, and basically what it is instead of using motion to generate current, you know, like a generator, you know, you spin the generator and it creates current. This one, you put current through that thing in the right way, and it'll produce a high velocity projectile. All right, now we'll probably get to that on Monday, how the railgun works. But the railgun's pretty effective, and they've been testing it. Supposedly it's about to be deployed, but they've been talking about it for. So look at that. That's a projectile going through a pretty thick piece of steel there, and just like it was, just like a 22 going through a soda pop can. But that's inch thick steel at least. Look at that up there. Anyway, so that's the railgun. Now I want to go to the document cam, and we're going to work out some of this flux concepts and then a flux calculation. All right. Not yet. I'll get down here. Okay. Could you grab a couple of pieces of papyrus from over there? Yeah. Go ahead and switch. Thank you. Oh. Yeah. My back is still fluxing. Let's just put it that way. All right, let me get my pencil down here. All right, here we go. PHY 2054 1025 19 star date something. Who knows what the star date is? All right. Now, what I want to show you is this whole idea of flux. So draw yourself a loop in kind of in perspective. All right. And we're just talking one loop. And I'm going to put a little. I'm going to race up here and put a little galvanometer in here. Okay, so we got a loop, and we put a galvanometer in there. All right, so, and I'll just, for perspective, I'll just draw in a X and Y axis like that. Okay, and then here's the Z axis coming out this way. All right, so there's our perspective view. Now, over here in the positive Z axis, let's put a bar magnet. And let's make this the end of the bar magnet. All right. Now, I'm not going to draw in the field lines. We know what the field lines look like. They shoot out of the N pole of the magnet, Lindsay. And, and they kind of spread out, like a dipole. But what I am going to do is put in two field lines, three field lines, one right through the middle. Now I'm going to put a dotted line here to indicate it's behind the loop. Okay, so there's one. So there's the central magnetic field line. All right. Now, slightly above that, I'm going to put kind of a curvaceous one to represent all right, so there's a dipole, and it's poking through right here. Okay. And the central one, of course, is poking through right here at the center of the loop. Now, for symmetry, I'm going to go down the same distance and try to do, okay, right about here. All right. Now, that's a little smorgasbord of the field lines that are poking through there. All right. Now, there's plenty of rightward poke throughs. All right. Now, this is a fairly realistic sketch, all right? Because, relative to this bar magnet. Now, the thing is to figure out the amount of flux, the flux is basically, let me do a little pixel here. So here's a pixel inside my loop. And what you want to do is figure out, how many Teslas times how many meters. So here's your magnetic field for one little, pixel of the loop, in the plane of the loop. Okay, so this is a pixel, single pixel, i.e. dA, in the plane of the loop. And this one's actually in the center of the loop because B is perpendicular to the pixel. Now up here, I'll draw another pixel up here. Here's another little pixel. And here, my B vector up here is a little bit of an angle. So let me draw. Okay, so up here, there's a little bit of an angle. So a realistic, all right, so here it is up here. So here's an upper pixel, like for right here, right? All right, so this little pixel, and then this one down here represents pretty much a pixel near the center, right down here. So every pixel is going to have a different angle. You're going to have magnetic field lines. They're going to be poking through to the right, to the negative Z direction. And you're going to have different components. And what the amount of flux is basically, let me do it down here. I'll make a big version of that second pixel. So here's an off-axis pixel. And let's put a dot in the middle of it. And let's put, for perspective, X and Y axis. And then the Z axis is coming out like this. All right. And the magnetic field, so this is off axis. The magnetic field vector is going to be like this. So let me, and this is kind of a blow up, or I'm doing a blow up down here of this one up here. All right, this off axis one up here. Okay, so this is a blow up, and let me do a dotted line to extend out. And this is the tilt angle relative to the Z axis, all right, for this magnetic field vector. So what you have to do is you take the magnitude of the vector, and that's B, and then you compute the component. So here's a side view of what we got. So here's B, here's theta, and this component here is the one that matters, B perpendicular. Okay, so that's equal to the magnitude of the full vector times the cosine of theta. All right, so there's a ton of trig in this. But you can average it and stuff. You got to use calculus and stuff. It's not too bodacious, but the main thing is you can say that there's some rightward field lines. Now, here's a view. Go down here now, draw a circle for your loop. And I'll put my galvanometer up here. All right. And here's my X and Y axis. So here's X, and here's Y. And I'm not drawing this. So this is looking straight down the down towards the negative y-axis. So what you can do, and this is what the textbook does, in order to allow you to calculate a flux, they assume an average value of b times cos theta, all right, b perpendicular, all right, and then they assume that you have the same value everywhere, all right. Now what that means is you have the same, they're kind of calculating a uniform, they're doing a little bit of cheating, but it is accurate if they do it with calculus, and they're assuming that you have a uniform size of magnetic field everywhere in the loop. Right now, uniform size means the x's are distributed uniformly. So now try to do what I'm doing. Try to fill up your loop with x's to symbolize B going into the plane. And let's see, I can get another one up here. Go over here. All right, see what you can do about, oops, that's not so good. Let's get down here. And on a computer, you could do this really accurately. Let's see if I can get one more out here. No, that's no good. I'll leave that alone out there. We'll get some more down here. All right. So uniform field. So it's an approximation. So basically what they're doing is say, all right, let me give you the average. I'll do the calculus for you. Here's the average. Assume you've got something like this. Okay. Now you don't really have this because you know that in truth, the field lines are going to be more concentrated at the center because that's where the field's going to be strongest. And toward the outer edge of the loop, the field lines are not going to be as crowded. So you have lower intensity out here. So this is like saying, all right, let's just, we'll calculate a good number and then we'll think of it as just a uniform intensity in here. All right. So the flux is equal to pi r squared times that B average. All right. All right. And remember, this B average has a bunch of calculus and trig in it stuff. Now, this is what flux is. Michael Faraday thought of field lines as being physical. We now think of them as fiduciary, but not physical. They're good for making calculations, but they don't exist in themselves. But flux is still a physical quantity that basically controls the induction, controls a lot of things, including the units of induction. Now, let's take a look at this for a second. The units of flux, I'll put it in a square bracket here. The textbook uses lowercase phi. I tend to use capital phi. Okay, we have some meters squared for area and some Teslas. All right. And we're going to use that in a few minutes when we calculate the EMF. Because Tesla is the same as newtons per amp meter. So let me just remind you, the units of the magnetic field, Tesla, are newtons per amp meter. All right. And we're going to relate that to volts in just a second. All right. So now let me pause for questions to see if anybody has questions about any of this. Okay, let's keep going. Andrew, can you swap me over to the laptop, please? All right. All right, so we got a dot cam image. Go ahead to the next one. All right, now this is from the textbook, and this reviews Lenz's law. All right, and the top image A is what I'm going to be talking about. The current will flow through the loop so that if you gain rightward flux from the magnetic field lines in this, and that's basically, what we were doing on the document cam a minute ago. If your loops are gaining rightward flux, then the coil is going to generate current in such a direction, it's either going to be clockwise or counterclockwise. And what the coil will do is generate a counter field, the opposite direction. So the magnetic field of the coil is going to be to the left. Now what that means is if the current's going to the left in this picture, it means it's going into the paper at the top and out of the paper at the bottom of this coil. Okay, it's kind of hard to see on this, but we'll try to do an example in a minute. All right. And I don't know what they have that right hand rule over there for, but that's what they got. All right. And students, this is called Lenz's law, that the coils always counter the change in the flux. So if you're gaining rightward flux, it's going to generate some leftward flux. And the current will be doing that. And that's the direction of the current. And my wonderful students, can you move this back? Use the backwards key. 1, 2, 3, 4. All right. Now, students, the minus sign in the EMF equation is from Lenz's law. Lenz's law says, all right, figure out delta phi over delta t, figure out how many loops you got, and then the EMF will produce the opposite of that. All right, and that's the minus sign. All right. So if you get some positive delta phi over delta t, the EMF is going to be negatory. All right. So it's going to produce some leftward delta phi. All right. Now let's push forward again. Go, 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 go. All right. So what we're going to do now is we're going to go back to the document cam. Go ahead and swap this to the next slide. Okay, and let's take a look at that coil. So here's my galvanometer. And let's put some X's in there. So it's gaining a lot of these. The closer I bring that bar magnet, the more I get of those. So it gains that. So the current will flow. Oh, sorry. Yeah. So here's what we're getting. We're gaining these inward flux arrows. Okay. And so the current's going to flow in order to produce these babies. Okay, so now what clicker question number 1. Oh. All right, and this is going to be, and it's not on the screen, of course. So this one is a short answer, and the question is, type in the direction of the induced current for this diagram. So a word or a phrase, and then hit the send key. No, Thomas, no. Don't use your left hand. Use this. See, you were just doing it.
Oh, no, I was just.
Oh, yeah, okay, yeah, you weren't doing that. Okay, good. No, of course not. I actually did that one time. Somebody caught me and they said, no, no, Thomas, no. You got to use the right hand instead of the left hand. Type in a word or phrase and then hit the send key. Uh-oh. I just closed it. Try it again. Everybody do your answer again. I just hit the wrong button. Type your answer in again. What word or phrase would you use to describe the current that does this, that produces that? This is a, yeah, so that, what kind of current will get you a B field, a secondary B field out of the paper? Type your answer in, make sure you get it, hit the send key. Aha, I finally see a correct answer. Aha. You can take off now if you want. I think we're good for today. Thanks for helping me. Yeah. 20 seconds. Starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. I see some good answers in here. There it is. Counterclockwise will get you upward magnetic field lines. Okay. So that's the direction of the current in the coil. Now it's kind of easy to see it when you draw your coil like this flat on the paper. And versus this one over here. Oh, I just tore it up. Nice going, Dr. B. This one over here, it's kind of harder to see it, but all right. Now I want to. Can you move my slide, please? I'm going to do another calculation here with you. Calculate. There we go. All right. What we're going to do now is calculate an EMF. given this hokey business of the average flux and all that stuff. All right. So we're going to say that the average flux starts out at pi r squared times 0.050 Tesla. Okay. And we're going to say that r is equal to 6 centimeters, i.e. 0.06 meters. All right. And so there's the flux. And this is initially. And that it changes to pi r squared from 0.250 Tesla. All right, so you're bringing your magnet a little bit closer, so that now at the final state you have an average of 1/4 of a Tesla for your average perpendicular field strength through the loop. All right. So that would mean, so in other words, if this is the initial picture up here with 6 X's going through there, no, 9 X's, then this one, then down here you'd have to draw the same loop with 45 X's going through there. All right, 5 times more. Now, delta T, the amount of time it takes is 1/10 of a second for the switch to close, or for this change to happen. Okay? And we're just going to use one loop. So n equals 1. All right, here we go. And let's do the EMF minus n times delta phi over delta t. Now we have everything we need to calculate that. All right. And hey, you guys, I'm going to go to just the absolute value of it, because we already know the direction. All right. So I have one loop. And then delta phi is final minus initial. So it's got a pi r squared times 0.250 Tesla minus pi r squared initial 0.050 Tesla. And then down here, 0.100 second. All right, so there's my calculation. And it's not too bodacious. All right, so I have a common factor of pi r squared. So 0.06 meters quantity squared. And then 0.25 minus 0.05 is 0.200 Tesla. And then down here, 0.010, oops, 0.100 seconds. All right, so these two become a factor of 2. And let's see, I get a, in the numerator, 1.131 times 10 to the minus 2 square meters for the area, and 0.200 Tesla, and then down here 0.100 seconds. Okay, so the EMF is basically going to be double this, so it's 2.262 Tesla meters squared per second. Now, is that a volt? I mean, Tesla meters squared per second. That's looking a little bit messed up. But we can get it squared away. We'll double check it here in just a second. Let me pause for questions, though, for anything that you need here. Anything that we've just done. Now, this is an example from the book, so you can double check it. And the textbook author explains it a little bit differently. So between me explaining it and you guys reading about it, then hopefully you'll get a good triangulation on this. Russell, good? What was that? It sounds like, I don't even want to ask what that sound was. Oh, that's a good alarm. That's what gets me up. I get home on a Friday afternoon to take a nap, and guess what? The next door neighbors, that's when their lawn guy comes with a leaf blower. And, you know. All right, so EMF is Tesla meter squared a volt. Tesla meter squared per second. Now let's check it out. A Tesla, as I mentioned before, is equal to a Newton per amp meter. All right. So a Newton meter squared or a Tesla meter squared per second is what we got here, is equal to a Newton meter squared and then amp meter second. All right. Now notice that I have meter squared on top and meter on the bottom. So this is going to give me a Newton meter on top. And an amp is a coulomb per second. And so Krishna, I have amp times a second. That's a coulomb. All right. All right, so there's Newton meters. What's a Newton meter the same as? What's the other name for that unit? Joule. So this is a joule per cool. And that, my wonderful students, is a volt. All right. Okay, so Mr. Andrew, can you switch to the next slide, please, and switch me over to the... Just wait, I'll stay on this for a minute. Okay, are there any questions about this calculation and this diagram up here? Anything that you want? Remember this is the idea. Faraday found this. And Lenz, Lenz is the guy that put in the minus sign, I guess. Some kind of a Russian, a Volga German. And so that's the thing. This is the key concept here. And I hope next week we'll do an electromagnetic induction with coils and bar magnets and stuff like that. Lab type activity. All right. Go ahead and switch over. So let's dismiss early today. And we're done. We just did a tough calculation, so you guys earned it. But hold on now. Audley von Ridley, I didn't dismiss you yet. Okay. 1 foot out the door. Is that why you sit back there? Make a fast getaway. Hey, I don't blame you. All right, so what I'm going to do, I'm going to give you an assignment with some flux and EMF calculations over the weekend. It should be fairly simple. And just keep reading in chapter 23. All right, you're dismissed. Make it break for it now. Quick, get away. All right, that's good. You should. Do you see her back there? She's like ready to dash out the door back there. Oh, it's all right. You sure can. What is your name again? Cassandra. Cassidy. Cassidy, right.